at every section. At every point of your beam, you have to draw the free body diagram. Okay, that is it.
Excuse me, sir.
Yes.
Sir, I had a doubt regarding the if the force is distributed over the beam.
Okay. Okay. So I am actually, so before we jump to the tutorial sheet, I am sharing a presentation which I would use when I was in the class. This I had done 2-3 years ago. Is my presentation visible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So basically we are trying to solve problems like as shown in the figure. Okay. This is a beam. The red color is the beam. The moving truck is like a load. And if you see, the beam is bending a little bit.
Sir, can you maximize the slide, sir?
So you see this truck, this red color is sort of a beam, red is the load that you're applying, and it is slightly bending.
Yes, sir.
And we want to actually find out how much it will bend, what to do, etc. But in this course, we will just find out how much the load is. How to calculate what the bending will be, what the shape of this will be is used to be part of the syllabus, but now it is not part of the syllabus. Okay. And I am not made a new presentation for you. I am sharing a presentation which I had used 2-3 years ago. But now all this is not needed. So what are we trying to do? Imagine that you have a beam, okay, something like this. It is subjected to different kinds of load. Basically, what you have to do is every time a new load is introduced, you have to make a section. Okay. And draw the free body diagram of that section and calculate the value of V, calculate the value of M. And wherever there is a load discontinuity, you will keep on doing that until you get the answer. The plot of V and M as a function of X is your shear force and bending moment diagram. That is it. So in this topic, we are only drawing free body diagrams. The first decision you have to make is where all do you have to make the cut? You have to make a cut every time a load is introduced. So this B is actually, if I remove the reactions, there is a load. So I have to make one cut here. Then this P2 has been introduced. So I will make another cut here. This W has been introduced. So I make another cut here. And this P1 has been introduced. I make another cut here. So I make 4 or 5 cuts. Every time I make a cut, I only look at the right hand side or the left hand side, draw the free body diagram, calculate the value of the reaction forces as a function of X, make a plot. That is it. That is all we are planning to do in this problem. So it's actually very, very simple. I mean, even you can write a simple code and it can do it for you. And in this course, we are only interested in 3 types of load: point load, uniformly distributed load, and moment. Nothing else. Okay. Be careful about the sign convention. The sign convention that we use is as shown here. Like as shown here. So if you are looking from the right hand side, then anti-clockwise moment is positive. If you are looking from the left hand side, clockwise moment is positive. If you are looking from the right hand side, downwards pointing shear is positive. From the left hand side, upward facing shear is positive. So you have to be very careful about the sign convention that you use. Okay. Or in other words, if a beam was straight and has tendency to go like it is, then that is positive bending moment. If it was bending the opposite way, like a mirror image of this, that is negative bending moment. The reason for choosing this as positive bending moment is that most of the times, if you have a bridge or a structure, it is likely to get load like this. It is likely to get load like this, and therefore my beam is likely to bend like this. This is positive bending of the beam. Now, if I had some other type of load, let's say it is like this, then my beam has tendency to bend like this. So green is negative because it is unusual for a bridge or a beam to get loading which is not in the direction of gravity. This is the logic behind our sign convention. So Whenever you solve any problem, my suggestion is draw this in the top right hand side of the paper that you are solving, so that you don't make any mistake in the sign convention. The only place where you can make a mistake in this very simple problem sheet is in the sign convention. If you understand the sign convention and you know how to draw free body diagrams, bus, this problem sheet is done. Nothing else is needed. Clear? Any questions?
Yes, sir.
Yes, sir, it's clear. Yes.
Okay. How? Yeah. So as I said, this is very algorithmic. It is almost writing a computer program. So let me show you how to do what. Suppose a beam is given to you and load is applied. How will you draw the bending moment diagram? Step 1, calculate the reactions at A and B, which I have done. Step 2, draw a section before every load discontinuity. These dotted lines are drawn. Step 3, either go right to left or go left to right. Draw the free body diagram of each section. For example, I'm going left to right. I'm drawing the free body diagram of section AD. It will look like this. Calculate and plot M and V as a function of X for every section. So for section AD, I found out that V is equal to half P, M is equal to half PX. Then I went back to step 3, drew the free body diagram of member AE of section AE, calculated M and thank you. Calculated M and V. Boom, done. That is it. So all you need to do is, as I have shown in my last slide, this 4 steps. So step 1 and 2 you will do it once. Step 3 and 4 you have to iterate for the number of sections that you have. And then you can draw your free body, and then you can draw your bending moment and shear force diagram. Okay, there is no trick, there is nothing is hidden. Absolutely, it is very, very algorithmic. As long as you understand, it can sometimes become very tedious, but it is very algorithmic. Even as I said, even a computer can do it. We don't need human intelligence to solve problems like this. So is this step-by-step algorithm clear?
Yes, sir.
Yes, sir.
Yes.
Yes,
So
sir.
Yes.
once you understand how this can be done, then you need to understand how the expressions for V and M will be for different type of loads. In this course, you have to worry about 3 types of load. Okay, which are those 3? So this is example of a point load. For a point load, these are how the expressions look like. V is equal to half P, M is equal to half Px. Now let us look at uniformly distributed load. So if force is continuous, you might say that one section is not enough. Should I make infinite number of sections? We don't approach it like that. We just take one section like I have shown, and in the left hand side, I draw the free body diagram of the left hand side of the beam, and I replace this uniformly distributed load with a point load at the center. Okay, so I have V is equal to minus Wx, M is equal to half Wx square. A uniformly distributed load can be replaced by a single load at the center of the section.
So center of this section or center of mass?
Center of the AC section. Na?
So please explain it once.
So like in my previous slide, I said that we are making a section as soon as there is a load discontinuity. Now, if there is a distributed load like shown in this figure, then you might say that I have to make infinite number of cuts, because every point is actually now discontinuity because load is being applied continuously, or on the other extreme, there is no load discontinuity. So what should you do? When you are looking at uniformly distributed load, you can make a cut anywhere where the distributed load is there. Draw the free body diagram of either the left side or the right side, and the free body diagram will look like this. Don't forget about this dotted arrow for the time being. Okay, so the free body diagram looks like this. There is uniformly distributed load V and M. We want to find out the value of V and M. To do that, this uniformly distributed load is replaced by a point load such that the magnitude is W into X. And that is the total load. W is kilonewton per meter. So I am putting W into X, that is the load, and that will pass through the center of this section AC. Now, if it is Wx, once I have replaced this uniformly distributed load by a single load Wx, then it's very easy for me to calculate V and M that I have already shown in my previous slide. Okay, understood?
Excuse
Sir,
me, sir. Excuse me, sir. Sir, if the uniformly distributed load is in a triangular shape, we replace
That is
it by 12 by
that
3 distance.
that is okay. So I will just tell you how to deal with different shapes, but it is not in the syllabus. Okay, it is not meant for first year students. So
Okay, so we have only this case.
only this case for uniformly this. So if it is like this or any other shape, not only triangular but any other shape, then this is replaced by a point load which is passing through the centroid of this shape. So for the triangle, it passes through, let us say, 2 by 3 into length x. If it was some other shape, it would always pass through the centroid, but this is just for your information only. For this course, it is not needed. For a uniformly distributed load where it was W everywhere, the centroid is the midpoint. If it was triangle, then I would have to find the triangle centroid. If it was some other shape, I can always find the centroid, but for this course, only focus on this case. This
Thank you,
is
sir.
for your information only.
Okay, thank you, sir.
Okay, so basically 1 minute. Coming back to our shape, this is what the shear force and bending moment diagrams will look like. W is equal to Vx, so it is increasing, decreasing linearly. M is equal to half Wx into x. So it is half Wx square, it decreases like this. Okay? And
Yes.
the third type of load that you will be interested in is this, that there is a point moment. If there is a point moment, this is how the shear and the bending moment will look like. So basically,
Sir, here we cannot move the moment at any other point like we do in other FBDs, na?
no, you cannot do that.
Yes, sir.
The resultant will be,
Different because of the cutting of sections.
yes. Tanmay is saying, sir gave the formula for finding the equivalent force and position of the application L1 only, I guess. Tanmay, I don't understand.
Sir, for the means for any other shape, sir gave the equivalent formula for finding its equivalent force and position.
I see. That formula is that it has to pass through the centroid.
Yes, sir.
Okay. So basically, this problem sheet is about remembering the table that I am showing. So if you remember that there is a simply supported beam subjected to a point load, this is what the shear moment looks, this is the shear force diagram looks like, this is moment. If it is constant, it is linear and parabolic, and if it is cantilever, this is what it looks like. Then basically any problem can be solved using a linear combination. The principle of superposition holds true, meaning to say that if I have a problem like this where it is subjected to 2-point loads, I could actually do the bending moment diagram all at once, or I could draw 2 separate bending moment diagrams for 1 point load each and add it up. Both are okay. So if you know how to calculate the bending moment diagram for point load, distributed moment, then whatever problem we have to give you has to be a linear combination of all three. And the principle of superposition is true. So make sure to understand how to calculate it for these three cases, and then you are done. Like for example, this is a good example. So let us look at this problem, okay? Now this problem, I have a beam which is subjected to a point load, which is also subjected to a uniformly distributed load at some point. Now, you know how to draw the bending moment diagram if only the uniform distributed load was present and if only the point load is present. You could draw both of them separately and add it up. Principle of linear superposition holds. Or if you are comfortable, you can solve both of them together also. But only these three things are there: point load, uniformly distributed load, and moment. Okay?
Sir, means by adding up, you means adding graphically, means both the graphs will
Adding
superimpose
graphically.
at
So
each point.
basically you are getting this, right? Let's go fuse. So let us say you are getting V is equal to Wx for V is equal to minus Wx for uniformly distributed load. And you would get V is equal to, let us say, P for point load. I need to
Yes.
say that, let us solve this problem. So let us say there was also another load P here. And no, sorry. Let us say there was also another load P here. So if only this load P was there, what would V be? V is equal to minus P. I mean, at this cross section, if I only consider the load P, then my free body diagram looks like this. V M. Let's call this V prime. So can I say V prime is equal to minus P?
Yes.
So the total V is equal to V.
Yes, sir.
Total V is equal to V plus V prime. So if there was a point load and a uniformly distributed load, you could solve it like that also.
Okay,
Okay,
sir.
sir. Got it. Got it.
Okay, so now,
Sir, can you repeat?
Sir,
yes.
sir, can you add the graph for moment MBD also? Sorry, BMD.
Everything is linear, na? Why you cannot add? Everything is linear. Principle of linear.
Sir,
Sir, moment is not linear.
Yes.
Sir, moment is function of x square.
You cannot add two uniformly distributed loads. You cannot say I am breaking my uniformly distributed, or you can do that also. Why not? It is square of x. It is not square of w.
Okay, sir.
It is not square of w, na?
So then we can add bending moment also.
It would be wx. So to m total would be minus wx square plus px. It is plus px or minus px. M is equal to, my fingers pointing downwards. 1 minute.
Sir, can you again explain this method?
1 minute. P is positive. So it's minus px, I think.
So minus px.
Minus px. So you can do. So this is basically the point I'm trying to make is, when we are dealing with beams, we are assuming everything to be linear. The material behavior is linear. The load application is very gradual. Everything is linear. So the principle of superposition is true. So to master this topic, my suggestion is that first try to master how to draw the bending moment and shear force diagram individually for three cases. If point load is applied, what will your bending moment diagram look like? If uniformly distributed load, what the bending moment diagram will look like? If the moment is applied, what the bending moment diagram will look like? Once you understand these three, it is essentially all the problems in this problem sheet are a linear combination of these three cases only. Okay, somebody wanted re-explanation of something. Which topic, which part?
So the present method you suggested different from the conventional.
No, this is This is also conventional. I'm saying that if you are faced with a situation where there is uniformly distributed load as well as point load, if both of them are there is no reason to get nervous, or there is no reason to get overwhelmed that there is more than one force. You know how to draw the bending moment diagram and shear force if only one type of load is there. If more than one type of load is there, all you need to do is you need to add up the shear force or add up the bending moment individually due to the two loads.
Excuse me, sir.
Yes.
Sir, here V dash is minus P for some reason only. No? After the point of action where P is acting. Before that, it will be 0.
Right. It will not be Px. It will be P into, good point, P into x minus L, where this length is L, small l. No, it is P into this length only. It is P into this length only. P into this length. You are
Sir,
right.
so we will make two functions piecewise, then add in the respective interval for moment and
We
t.
will.
Yes, sir.
We will always calculate x from the same point. X is measured from the same point. There are actually some books suggest this, but I think that leads to a lot of error. Some book says that whenever you make a section, start the x coordinate axis system from there. So they are saying that for this, so it is getting clumsy. Let us change the pen color. So let us say you made a section here. Then it is said that you should start from x. And let us say you made another section. Let us say you made another section here, and then you measure the x from here. This is very confusing. It will lead to a lot of errors. My suggestion is that always measure x from the tip. Don't, every time you measure, every time you make a new section, do not change your coordinate axis system. Don't change the value of x. X always measured from the tip. All your equations for v and m will come out to be very consistent. Much easier. I think it is not, I am assuming that what I'm trying to say is not clear. So let me make a new slide and let us try to understand what I'm trying to say. Okay. Now, imagine I have a beam. This is P by 2. This is P by 2. At the midpoint, we have put P. Now, where, and let's call this A, B, C. Okay. So now the first section will be made here. So let us go for some other color. The first section has to be made here. The second section has to be made here. Let us look at section A. Let's call this AA prime. Section AA prime has P by 2, and we have our normal V and M I'm calculating. Now we can do this. We can now, X is measured from here. Okay. Next, I have to draw for, let's call this B prime. Now I have to draw for AB prime. Let's draw it here. This is AB prime. I have P by 2. I have P. Again, I have to measure X from here itself. Now I am not measuring X from here. This is not right. X is always measured from the same datum point. If you start measuring, if you start changing the datum point X, then your equations will be a little bit difficult. Yes, Tanmay is right. You follow the absolute system, not incremental coordinate axis system. Clear? I think best
Yes,
is
sir.
that try to solve a few
Yes.
problems. Let's try to solve a few problems. I don't think it is very difficult. So, do you have the problem sheet which I have uploaded today?
Yes, sir.
Yes, sir. Yes.
Yes, sir.
Okay, so let us look at problem number 2. Okay, this is only bending moment diagram, but slightly different from the problems that I have discussed because it has the
So
uniformly
I have a
distributed.
question. So
Yes.
I have a question regarding the previous topic. So can I ask after the end of this lecture?
We will have, I think, one doubt clearing proper based on whatever the topics are for the second exam. Okay.
Okay, sir.
This is about friction, is it?
Yes, sir. Mainly screws, that part.
Yes.
One thing I was not getting. That's
Professor Maiti is working on an additional handout also, so hopefully it'll help you.
okay, sir.
Okay, so is my slide visible?
Yes, sir.
Yes, sir.
This is the problem. These
Yes,
are
sir.
step by. This is the problem. These are the step by step. Let us go for it. What are the reactions at A and C? So for this, it should not be C. What are the reactions at A and C? Can anybody tell me quickly?
So 4.5 and
So
1.5.
4.5 at A and 1.5 at C, sir.
4.5 kilonewton. Okay, unit is important.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir. Kilonewton.
Yes, sir. Kilonewtons.
Kana mama.
1.5 kilonewton. Now, step 2 is draw a section at before every load discontinuity. So now that I have replaced this, I should actually replace the constraints by load before every load discontinuity. I must draw a section. So where do I have to draw a section? I have to draw a section between A and B, because after B uniformly distributed load is not there, so that is one discontinuity.
Yes, sir.
And at C there is a point load, so I have to draw another section here. So step 2, I have decided that I want to draw the two sections as shown. Now let us draw the free body diagram of AA prime, where this section has been made at A prime. You can either go left to right or right to left. Let us go left to right. And we also have to keep in mind, 1 minute. We have to keep this sign convention in mind. So now go for it. I think you should be able to solve it. Draw the free body diagram of AA prime. There is a point load here. There is a point load here. There is uniformly distributed load everywhere. Now find out the value of V and M as a function of X. Please do that. By default, I'm assuming that my V and M are positive. If I get negative value, I will write negative value.
Sir, V will be 4.5 minus 3x kilonewton, and M will be 4.5x minus 1.5x square.
Yes.
Kilonewton meter.
Correct. Is your sign convention right?
Sir, it will be for 0
Yes,
to
sir.
2.
It will be what?
For 0 to 2, na, x equal to.
X is varying from 0 to 2. Yes.
Yes.
Yes, sir. and it will be 1.5 for 2 to 4 and minus 1.5x plus 6 BMD for 2 to 4.
Now similarly draw a section CC prime where x is varying from 2 to 4.
Sir, I have a question, sir.
Tell me. Yes.
Sir, when we are considering the section from 2 to 4, can we replace this uniformly distributed load by a single force at its center of section, or we
Yes.
cannot do that?
Yes, you can do that. For calculating, yes, for both you can do that.
Means I am taking a point means section AC dash. So I will replace this entire uniformly distributed force by a single force of 6 kilonewton acting at a distance of 1 meter from A.
Correct. Yes, that's right.
And V and M will be same.
Yes.
Okay.
Please try to solve this. This is a very simple problem. I would like everybody to solve it. And you can please confirm whether you are getting this. This is solution that I have got. My computer has hung. Yes. Hello, can you hear me?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Sorry, my computer misbehaves from time to time. Yeah, so this is the solution that I am getting. Can anybody confirm?
Yes, sir.
Yes, sir. Same I got, so.
When you draw the bending
Yes,
moment
sir.
diagram and shear force diagram, it is very important to do a few things that I am doing here. One, the point where the bending moment diagram is highest. This should be clearly marked. This is one. And two, where the nature of the curve is changing. So this is somewhat like a parabolic or non-linear till here, and after this point, it is linear. So what is the value of bending moment at the point of inflection? These two things you should write. Similarly, for shear force, what is the highest value? What is the lowest value? Plus and minus. Writing this is very good habit.
Yes, okay, sir.
Please keep this in mind. This is because a common question is not to draw the bending moment diagram or shear force diagram, but where is the maximum value, what is the length, and what is the location.
Sir, in our objective type question also, this type of questions will only come, like finding out the maximum value and the position where it is obtaining it.
No, it can also come that we will draw 4 and you have to choose which one is correct, and there will be very
Oh,
small.
yes, yes, yes. We have MCQ.
Or it could be at section this is equal to this. What is the value of bending moment?
Your call is being connected.
Okay. Clear?
म्यूजिक ऐप इंस्टॉल करें।
Yes, sir. Clear, sir.
हेलो बोले आ रहे हैं यहाँ।
Now let us look at our problem sheet once, okay? So if you look at our problem sheet, I think question number 1, 2, 3, 1, 2, 5, 6. No. So far, so is it correct from my side to assume that all of you know how to draw bending moment diagram if there is a uniformly distributed load or point load?
Yes, sir.
So based on that, I can say that question number 2, question number 5, and question number 8, question number 7, and question number 10, all of you can do. Correct or not?
Yes, sir.
Yes, sir.
So let us do something. In the next 10-20 minutes, try to solve. How about try to solve question number 5, everybody? If you have done 5 and 6 are very similar, 5 and 7 are very similar. If 5 is done, try to go for question number 10. So solve question number 5 and 10. If you have any questions, ask me.
Sir,
Yes.
can you show the second number solution again?
Is it visible, my PPT?
Uh, yes, sir. Sir,
Yes.
sir, after the B point, it is a straight line, right?
Yes.
Okay, sir. Thank
Shear force diagram is straight and this bending moment is inclined.
you. Okay, sir.
And one way of checking whether your solution is right or not right is by noticing, and I think Professor Sushanto Chakravarti has also mentioned it in his video, that if you integrate one, you get the other. That the bending moment diagram and shear force diagram are not independent of each other.
Yes, sir.
So that is one way of checking it. Usually my prescription is that you try to do it normally, but use that knowledge for checking whether or not your solution is correct. Okay, so please solve question, as I said, please solve question number which we said 5 and 10, yes? Please solve 5 and 10. If there is any doubt or anything, please let me know. Let us take a snip. Let us. Okay, so please do it step by step. What are the reactions? Tell me, tell everybody.
Sir, at the
7
pin
and
it is
13.
7 and 13.
2 into 12 is 24. 24 plus 8 is 30. 17 and 13 you are saying, yes?
7 and 13.
7 and 13.
7 and 13 is 20.
Ye-
But
Yes, sir.
I am getting
6 into
16
2
at
is
both.
27.
Sir, I'm getting 16.
I don't
Yes, sir.
16,
I am
16,
also
sir.
getting 16.
Same here, sir.
Yes, sir.
Both
I
Yes,
am
sir.
16.
also girls is
16,
16 and
16 is
16.
correct.
So because I mean 7 and 13 means that the total load is 20, but 2 kilonewton is for 12. So 2 into 12 is 24 plus 8 is 32. So the
32.
sum of both the reactions must
Yes,
be
sir.
32, not 20.
Yes, sir. 16 in
Yes,
both.
sir. 16 and 16 are coming, sir.
Okay.
Both.
So let us say
Yeah,
most of
sir.
16 and 16. Okay. Where will we make the sections? How many sections?
So 3 sections.
1, 2, 3. Yes or no?
Yeah. Yes, sir.
Okay. Now please go ahead. Try to solve.
So can you mark them section as so that it will be easy to us?
Okay, done. Any progress? Are you getting this answer?
Sir, I got the SFD right, sir. Can you please tell how to make BMD
Yes, sir, got it.
quickly?
How to get BMD? Yes, what is your question?
Yes, sir. How to make BMD quickly, sir?
Quickly, is the same proposal in the same option. You are getting per section, you are getting some equation in terms of x. Okay, and it for the limitations in this class, it is either going to be straight line or it is going to be x square. And you will draw this. I mean, it is not expected that the BMD that you draw will be to scale. That is not our expectation. Expectation is basically you should be able to tell whether it is linear or non-linear and what is the maximum value.
Yes, sir.
So, I mean, your question is how to calculate the expressions of BMD quickly or how to draw it quickly?
No, sir. How to get the diagram correctly, sir? BMD diagram. Sir, SFD is easy to get, sir, but
basically, it is only going to be a square term in x. Either it is BMD is either going to be linear in x or square in x. for the cases that we are considering. It cannot be anything else. Keep that in mind, then I don't think it'll take. And we are not expecting a two-scale diagram. We should be able to differentiate between whether BMD is minus or plus and what the maximum value is. That is one option. The other option is that you draw the SFD using the method that we discussed and integrate to get the BMD. That is also okay. Okay, does this help you?
So can you just repeat it once more, please?
I was saying that one more possibility is if you find drawing BMD difficult, why don't you draw the SFD using the method that we have discussed and section by section integrate to get the value of BMD?
Okay, sir. Okay, sir.
Sir.
Yes.
In the last part, CD part of the BMD, I am getting a linear curve, not a
Yes, sir.
parabolic.
That was a
That is
straight
linear.
line, right?
This is linear. This is linear. This is
Okay,
straight.
yes, sir.
This is straight, so linear. You get curves like this only when there are uniformly distributed loads.
Okay, sir.
Okay, so if you have done question number 5, very good, go for question number 10. If you have not done question number 5, please try to solve it and make sure you are getting the same answer as I have got before we go to the other type of problems. I'm sure everybody has not done question number 5. Out of maybe 140, 150, 50, 60 have done. For the other 100, please make sure that you have understand how to do this question 5 and confirm that we have got the correct answer. The ones who have got it, please go to question 10. Question 10, yes.
Sir.
Yes.
Sir, between B and C, the graph is parabolic, na?
More or less, है ना? B and C.
Yes, sir.
Between B and C, there is no point load, so it has to be parabolic.
Yes, sir. I was just confirming.
Question 10, Tanmay. 10 is done?
So 5 done.
After 5, go to 10. 5 and 10 are very similar. Just a question of practice. By looking at the bending moment and shear force diagram, can anybody tell me why we define beam as a member whose length is very long?
So what did you tell now,
So
sir?
I am not telling you, I am asking you. So
Yes, sir. I didn't get the question.
the question is that imagine that you have a simply supported beam subjected to point load, and we define the beam as a structure whose length is very long. By assuming that the length is very long,
Sir, because we can compared to the bending and the shearing force, the
Sir, strain will be very small.
the twisting and the axial forces are very negligible.
that is right. That is absolutely. What is your name?
Ram.
Very good, Ram. So if you have a short member, the shear force, if you only apply a point load, shear force is independent of the length. It comes out to be some solid value. Like, let's look at it. Let's say this structure. So this is a beam subjected to point load. Shear structure is independent of the length. Moment increases linearly as the length increases. So if this structure is above a certain length, the only dominant load on this is bending moment. So those members which are predominantly only subjected to bending moment actually are called beams. That's why in his lecture, in the lecture that we have got, I think a statement was made. A beam is typically length is 5 times the radius. 5 times the radius because bending moment is increasing linearly as a function of length. Shear force is not increasing. So if my member is very small, mostly it is getting only shear load. If it is very long, it is only getting bending moment. And beams are members which are designed to take bending moments only. Therefore, we are making this statement that we'll call it a beam only if the length is significantly long. Clear? Understood, everybody? Yes or no?
Yes, sir, got it.
This is
Yes, I got it.
This is a very common question in Viva and job interviews, especially if you belong to mech, aero, civil.
So sorry, sir. Please, can you repeat again that part, sir?
I'm saying that look at this case, okay? If you have a member which is subjected to a point load, the bending moment and shear force diagram looks like this. The shear force is independent of the length. The bending moment is 0 at the tips, increases linearly. So if the length was very small, then the shear force is dominating the bending moment. If the length is very long, then the bending moment is the only load that is going to be very high. The other loads are going to be small. So beams are members which are designed predominantly to take bending loads by definition. Therefore, we say that if the word beam is used, it means that the length is much longer than the cross-sectional dimensions. In that case, the shear force is low, bending moment is very high.
So got it, sir.
Okay, good. Question number 5, anybody who could not do this or anybody still has any more doubts in this? Okay, if not, then let's look at question number 10. Once again, let's repeat everything. What are the reactions at B and D?
Sir, at B there reaction will be 5 kilonewton at 5 and at D at 1.
Will be 1.
5, 1, is it?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Next, where will we make the sections?
Sir, between A and B.
B, C, and CD.
A, B, B,
Yes.
C, C, D.
Okay.
3
Okay. Good. Okay. Then now just go right to left, left to right, however you want, and draw the free body diagram for each section. Just make sure to keep this sign convention in mind. I have posted the correct answer. Please have a look.
Yes, sir, I am getting the same graph.
Okay.
Sir, I have a doubt, sir. Here
Tell me.
means, how can you explain the discontinuity in shear force? Means that is
It is actually, it is not. I mean, we are drawing it like this, but there is, because some load is applied at that point.
means we cannot define the shear force at the point
Actually,
where load is applied.
actually, this straight line should not be there. It should be this. In some books, they don't draw this straight line. They draw this as dotted lines, and they say that this location is A minus delta, this is A plus delta, and this is dotted line. Some textbooks which are very particular about it, they tend to do this. So it's nice catch. Yes, I agree with what you're saying.
Means we cannot define shear force at a point where load is applied. Means at that point we cannot calculate.
But in reality, you can never apply a point load. It will be load at a certain distance. And it will
Yes.
be, so it is, in this case, it is A minus delta and A plus delta. So this is actually A minus delta length. This is A plus delta length. And some books, they draw this as dotted lines, not as solid lines like we are doing it.
Okay, sir.
Okay, good. So everybody understood if point loads or if uniformly distributed loads are there, how to draw the bending moment diagrams?
Yes, sir.
Yes, sir.
Yes, sir.
Good.
Got it.
Good.
Sir.
I am happy. So now let us look at, let us
You have solved all our doubts.
I'm glad. So I think the topic is not over. There is some difficult topics. So I will take your compliments after all the topics are clear. So now let us look at this problem. One minute. Now let us try to understand what will happen if we have a bending moment at a point. Okay. So it is something like this. I have a beam which is overhanging, subjected to a bending moment at a point. So how will we do this?
Sir, could you repeat the question once again?
The question is that so far we have discussed how to deal with point loads, how to deal with uniformly distributed load. And in the syllabus, we have a third type of a load, which is bending moment, M1 as shown in the figure. Okay. So how do we calculate the bending moment and shear force diagram in cases like this? So it turns out that the process remains exactly the same. Wherever there is a bending moment, you will have a spike in your bending moment diagram. So again, I will first calculate the reactions. Okay. Then due to the bending moment, there is a sudden incremental, there's a sudden jump in the bending moment diagram. Rest of the things remains exactly the same. So this bending moment diagram causes no shear. If you apply a bending moment, in the bending moment diagram, there will be a sudden jump in the value of the bending moment. Rest of the things remain exactly the same. Clear or not clear?
Yes, sir, clear.
Yes, sir.
So again, this is only the third load. So these are the only three types of load, and perhaps bending moment is actually the simplest. You only have to be careful whether it is positive or negative.
So, but practically, how do you apply a bending moment without applying a shear force?
Let me show you in the next slide. I will show you. Okay, since it is in this phase, this is positive. So the reactions will be, this is actually negative bending moment that has been applied. So this is minus. Okay, so how can we apply bending moment at a point? So this is how, one way of doing it is this. Now I am looking at problem number 9. How will we solve problem like this? So this is a beam, and in the beam 2 hooks are kept. Okay, and you are applying load to the hook.
So the force at them, which is 5 Newton, they are just providing the moment at the respective point.
They will do both. So at this point where there is intersection, at the, thank you.
So can you explain what is rigid bar? I didn't. I'm not unable to visualize it properly.
Okay, okay, 1 minute. So let's finish this. Then I'm coming to rigid. Okay.
Yes,
so
sir.
this way there is a beam, and there are some rigid. Oh, okay. Sorry, this question itself, the rigid bar is there. Rigid bar is a bar whose modulus is much more than the beam. So this bar in itself is not going to deform, or nothing is going to happen to this. It is rigid. It is not going to bend or nothing. I mean, its stiffness is much higher than the beam. Such members are known as rigid bars. So its only job of this bar, which is rigid, is to somehow we are applying the load in the rigid bar, which in turn is getting transferred to the beam. So how will we solve problems like this? So this 5 kilonewton will be replaced by a 5 kilonewton point load here, and a bending moment of 5 into 1. So 5 kilonewton meter. Okay. Are both the questions clear? What is rigid bar? Is it clear? And how we deal with this problem? Is it clear or not?
Sir, I understood how we deal with it, but could you explain once more that what is a rigid bar? I didn't get that quite well.
A body is said to be rigid if its modulus, if it is Young's modulus, is very high. What is Young's modulus? Young's modulus is an indicator of the deformation, or Young's modulus is the load that you have to apply so that the length of a body gets double. That number is known as Young's modulus. So if the Young's modulus of the bar is much higher than the beam, then it means that this 5 kilonewton load is going to have no effect on the rigid bar. It is only going to affect the beam.
Okay, sir.
Excuse me, sir.
Yes.
Sir, I didn't understand how you wrote the reactions of rigid bar on the beam. Do we have to separate the rigid bar and beam to know what are the forces which are acting on the beam because of we are applying force on rigid bar?
So this rigid bar 5 kilonewton, this 5 kilonewton, apply it at the point of contact between the beam and the rigid bar. 5 kilonewton plus 5 kilonewton into 1 meter moment we have to apply.
So why aren't we applying the 5 kilonewton right below where it is applied?
No,
Why
but
do we have?
the contact is, the beam is getting the 5 kilonewton through the rigid bar. That's why.
Excuse me, sir.
So we have to apply at the joint point.
Yes.
Okay, sir.
Excuse me, sir.
Yes.
Sir, but for this we will have to draw the free body diagram of them by separating them, right? Because we have to find what are the reaction forces. Like I didn't get how you directly told where the like force and the moment will be there. I didn't get that.
Okay.
Directly.
So let's do something. I'm sharing something. 1 minute. Please hold. Is my presentation visible?
Yes, sir.
So
Yes, sir.
what I have done is that this rigid bar has 5 kilonewton. Okay. This, I have erased this rigid bar. 5 kilonewton into 1, 5 kilonewton meter is applied, and this 5 kilonewton is applied at the joint. Similarly, at point E, this 5 kilonewton load is applied and 5 kilonewton meter bending moment is applied. 5 kilonewton is 5 into this distance. After applying this, then I will calculate the reactions RA, RB. Okay.
Yes.
Let me go full screen. Now I think it will be visible, all the details.
Hello, sir.
Yes.
Sir, due to the right side rigid bar, that 5 kilonewton force should be pulling upwards or not?
No, it is, I think, correct. It is anti-clockwise bending moment.
And sir, we are also applying 5 kilonewton force.
Force you have to apply. So you are basically, remember
So
what we have
force
learned.
remains in same direction.
Force remains in same direction. Remember what we have learned in first problem sheet, that if a point is applied at if a load is applied at a point, you can convert it into a force and a couple at some other point.
Yes, sir. Yes, sir.
It is the same thing.
Okay, sir. That's what. Okay, sir.
Okay. Now that the equivalent figure is given, can you draw the bending moment and shear force diagrams? The resultant is also given. Now, can you do it?
Yes, sir.
Yes, sir.
Go for it. Why not? So this is one section I will make here. 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 Keep in mind that this bending moment that is applied here, this is also a load discontinuity. So I have to draw another section after that also. So 4 sections. It will take some time, but go for it, I think. If you get this right, then more or less you can be confident about this, because this specific problem has all three together. All three as in all three types of loads.
Excuse me, sir. I had just one doubt.
Yes.
Sir, like here we have like three forces. Like if we combine the 8 kilonewton one, so 8.
No, I lost you.
Since we can find the resultant of these three and apply at one point, sir, can we do it for the moments also? Means anything like this for moments?
Can you repeat? I think part of your audio was lost. Please repeat your question.
Okay. Sir, I was saying that we have three forces, 8, 5, and 5. Now, as we can combine these three forces in one single force at some point, can we do the same for moments also?
In this context, I think in the context of bending moment diagrams, the location where the bending moment is applied is important. You cannot, it is not a free vector anymore. You cannot treat it as a free vector anymore.
So I am not saying it is as free vector, but can we add the two forces, like we can apply the center of mass formula for these three forces?
Which three forces? So you are talking about 8
So 8, 5 and 8, 5 and 5.
So are you talking about these three? 8, 5, and 5.
Yes, sir.
So
Sir,
these three,
now,
you want to
yes,
take
sir.
only one section, is it? You don't want to make this section. You don't want this section. You only want this section. Is this what you were
Yes,
saying?
sir.
No,
Yes, sir. Only we'll replace the three forces by one force at a single point. Like we'll
okay.
find that point.
No. In member A and C, this bending moment and this 5 kilonewton and this 5 kilonewton has no effect in the region AC.
Okay,
So
sir.
you cannot. Don't complicate unnecessary. Makes no sense. Maybe what you are saying might lead to an answer by a long-winded circuitous route, but my advice is don't go for complex things unnecessary.
Okay, sir.
Complicate only when needed.
Yes, sir. Sir, because I thought if there is only one force and one moment, then it will be much simpler.
Much
So I
simpler,
thought,
but no.
okay, sir.
So I don't get why is there an additional moment, clockwise moment of 5 kilonewton meter in at the end, in the below.
You did not understand this part. This 5 kilonewton meter. This
No,
arrow.
sir.
This is because
The, the
this load is applied at a distance of 1 meter away from the point of intersection. 5 into 1 is 5 kilonewton meter. We are replacing this point load with a load and a bending moment. Remember in the first lecture you have learned, the first topic.
Yes, sir. Yes, sir.
Got it?
That was not the question. Yes, sir. That was I mistook something, sir. That the swirling arrow is there, so I thought that was an additional moment. So the picture selection, that one, I
Okay.
mistaken.
Understood now?
Yes, sir. That I had understood. I mistook that arrow of the selection as something.
I see.
As an ex-
Okay. Good.
Sir, there need to be 4 sections.
Yes.
Oh, yes.
As I said, this uniformly distributed load, even though it is uniformly distributed load, this moment and this applied load that is there, 5 kilonewton, 5 is a load discontinuity. So I have to make another section. The second section will be there. Though we will not do as a part of this course, but I can tell you that from the bending moment values that you get, you can directly calculate the stress in the beam, or you can also calculate how it is going to deflect.
So accordingly, then after we have to choose the materials for different purposes and for bridges, chassis designing, and all. Right?
Yes, but more than the material, the first thing as a designer, the first tool that you have is you will decide the cross-sectional shape. It also depends on what's the cross-sectional area.
Yes, sir.
First, you will change the cross-section. If you still cannot get it, then you go to the material supplier and say, I want some other material.
Yes, sir. I got it.
I have projected the answer. Please check and confirm. Due to the bending moment, as I said, there is a jump in the bending moment. Due to the applied bending moment load, there is a jump, which you can see here, and which you can see here.
Excuse me, sir.
Yes.
Sir, I also see sometimes there is a discontinuity at a load point and sometimes continuity.
I don't understand. What sometimes there is?
The value at points are same, and left hand here and right hand here.
It is actually slightly, theoretically, this is not correct. This line should be dotted line. And this is the 6.75 kilonewton is at C minus delta, 1.75 is at C plus delta, where delta is very small but not zero. Actually,
okay, sir. In mathematical term, we will say there is a dot at that point.
Yes. But
okay,
I mean, if you
function is not defined at that point, but limit is same.
Yes, if you follow very strict textbooks, they will say that this should be dotted line.
Okay, sir.
Yes, sir, I'm getting the
Excuse
same
me,
answer.
sir.
Yes.
Sir, can you please explain? I'm not getting this part, which is from 15.625 to 15.75. This hum.
This one.
So in BMD, where the value is the highest point of the BMD, that point.
This is coming due to the fact that there is uniformly distributed load here. Where there is applied bending moment, this jump from 10.75 to 15.75. This is this 5 kilonewton meter. And then at this point, so from C to D, what can we expect? From C to D, there is 8 into half into 8 into x square. Let me do this. Control P. So let us try to draw. Let us draw a section here and let's try to solve it here. Okay. And we want to find out V. We want to find out M, and this is subjected to.
So I'm getting the same answer, sir.
Okay, let us, for the benefit of everybody, let me try to solve this. So at this length, M will be equal to what? M is equal to this load, which is RA into X, okay? Then this
Yes, sir.
8 kilonewton meter into half X square.
Yes, sir.
This 5 kilonewton meter and this 5 kilonewton into X minus 1.
Yes.
5 into X minus 1. Doing all of this together, you are getting this shape. This. Understood? RA into
Sir,
X. Yes.
what you told by that equation, there is no jump, sir, at the point.
Yes,
This
sir.
jump,
I'm also not getting that heap part where
this part. Are you talking about this jump?
so your cursor is not visible.
Yes, sir.
I was
Train
drawing
is
it.
stagnant.
This hump you are talking about. Is my pointer visible now?
No, sir.
No, sir.
No, sir.
No, sir.
Just 1 minute. Let's do something. Which hump? Hump AB, BC, CD or BD?
So in
CD
BMD,
part, sir.
the CD part.
CD is coming because now when you are drawing the bending moment diagram, as I have shown in this, in the red sketch that I have drawn, there are counterbalancing factors. Some are leading it to increase, some is leading it to decrease. Once the increasing part, once the bending moment which is having negative value starts having a dominant effect, it will start to decrease. As I said, there are if I draw this section which is shown at the top, there are, how many terms are there for the bending moment? RA into X, half 8 into X square, 5 kilonewton meter, plus 5 into X minus 1. Some of them are positive, some of them are negative, and all of them are depending on X. So as the value of X increases above a certain limit, the trend of the curve will start to decrease. That's why you are getting the value is coming down at CD. And at D, suddenly the curve changes nature because the uniformly distributed load disappears after D.
Okay, yes, sir. Thank you.
Okay. Everybody or most of you have got this answer?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay.
So,
Yes.
so in this diagram, the peak value in the BMD, sir, at C, we have to mention, sir, at what X equal to.
It is not mentioned here. You should mention ideally, yes.
Okay, sir.
That you will do dx by dm by
Yes, sir.
dx is equal to 0.
Yes, that is equal to 1.2 something.
Okay, could be. 1.2, between 1 and 2, some value you should get. Okay, now the last topic that we have to discuss in this is what is known as hinge joints. Okay, this is the last
Yes, sir.
variant of problem that we have to discuss. This is question number 4. That is the last type of question. Okay, is this visible?
Yes, sir.
Yes.
So a hinge joint is actually a two beams which have been connected at a point. This is the concept of a hinge joint. Understood? This circle that you see here is a hinge. Hinge basically means that there were, let's draw something. Where is that shape? That this is beam 1, this is beam 2, and both of them are connected by a pin. Okay, so a hinge joint basically is beam 1, beam 2, both of them connected by a pin. If it is connected by a pin, what can we say about the reactions at this point? When two parts are connected by pin, which component of force or moment is zero?
Moment is
zero. So basically, if these are two beams are joined at the center. You can draw the bending moment diagram of the two parts separately. And as a check, you have to make sure that where there is pin, bending moment must be zero. It is actually two beams joined together, and at the point of joining, the bending moment is zero. That is it.
Sir,
Yes.
sir, the roller joint at that part, if you are going to find out the force, then at first, without removing the hinge part, can we calculate it?
No, then it is statically indeterminate.
Okay.
Look at the number of unknowns. There are 4 unknowns.
3, sir.
Why?
Sir, I'm saying that we are not saying that the hinge force is accounted now because we are not separating the two bodies.
There are 3 unknowns, but all the forces are parallel, so you can only calculate for 2 unknowns.
Oh, okay. Yes.
So break it into 2 and then you can solve it. It should not be a problem. Just keep in mind.
I could not understand about the open hinge. Oh, internal hinge.
Internal hinge. So let us try to first understand why internal hinges are made. Okay. And then we will discuss how to evaluate it. Okay.
Okay.
So for that, let me take a few figures from this slide.
The internal hinges are not the ones that are used for open bridges that open for certain ships.
That is some locking mechanism, I think. But
Sorry.
yes. Snip. Let us take a snip. Okay, now let us look at this figure. Okay, for the time being, don't look at this. Don't look at this. Look at only this blue figure that I am drawing. Okay, so I have uniformly distributed load, and I have, now I know that the bending moment diagram will look like this. Okay, this we already know. Now, at the peak, you can imagine that the bending moment actually can be quite high. Yes, if the length is very long. Now, imagine that we put a hinge somewhere at the center. Okay. Now we are saying that the hinge, due to the hinge at the center, the bending moment actually has to be zero because it's a hinge. So what will my bending moment diagram look like? It's actually going to look like actually going to look like this. It was this blue figure to start with, but by introducing a hinge, I am actually, you can imagine it that we are trying to pull down the bending moment to be zero at the hinge. So now the bending moment diagram is going to look like this red line. So hinges are a wonderful means of decreasing the bending moment at some points. So this is why we use hinges. From a design point of view, this is the reason. Is it clear? Do you understand why the bending moment diagram will look like the red line?
Yes, sir.
Because at the hinge, the reaction, the bending moment has to be zero.
Yes, sir.
Yes, sir.
This is a wonderful way of reducing the bending moment. Now, how do we analyze it? That is the second part. To analyze it, we will break our hinge into two. We will treat it as if they are two independent beams. Okay? With the knowledge that at the hinge, the bending moment is zero. Draw the bending moment diagrams for the two beams independently and then later on join it. Yes, understood or not?
Yes, sir.
Please try. Let I think Professor Sushanto had also put a file.
Sir, will there be a shearing force at the
Yes,
hinge?
yes, yes. It's a pin joint. Pin joints allow.
Okay. So there'll be a reaction force at the hinge.
Yes, yes, yes. That reaction force will be there.
Will
Sir,
be
in this case, our coordinate system will be two.
You can make it two coordinate systems. You draw the free body diagram, draw the BMD diagram completely independently.
No, sir. If we take single, then we will get two different curves.
Wait, I don't understand. Ek minute. So, how to share? So, I'm saying that draw the BMD of this independently. And draw the BMD of this part independently. Okay. At this point,
Taking that at new origin.
New origin. So this is one beam, independently make it. So you will, hopefully you will measure X from here for one case, and for the other case, you will measure X from here.
So if we take single coordinate, then our answer should be same.
Even if you take the same coordinate axis system, but when you are analyzing this beam, which is under the green box that I have drawn, you have to write the expressions carefully. That everywhere it will be X minus 2.
Yes, sir. I think Taylor series will work here. So it will.
If you do X minus 2 and if you do it, if you are careful, there is no doubt why your answer should not be correct.
Okay.
Sir, even without separating, we can solve it.
By enforcing that your M is 0 at the hinge. Yes?
Yes, sir. Yes, sir.
How will you find the reactions at the two roller and the pin?
Sir, R1, R2, R3, we get a y direction equation. Then moment conservation about the middle hinge, we get relation between R1 and R3. Then first roller at the first roller we will conserve moment again. We will get the relation between R2 and R3.
No, sir. We get only two equations, sir.
Two equations, no? You need three equations.
Yes, sir. Yes, sir. We have to consider the
No,
separate
no.
part.
The third equation is that the three reactions sum has to be equal to 10 into 8. Ra plus Rb plus Rc is equal to 80.
Yes, sir.
And yeah, so basically two equations of equilibrium. The third equation is that at the hinge the reaction is 0.
Yes.
But no. That is the reaction.
No, sir.
It doesn't
I'm
mean
saying
that if you it doesn't mean that you take the moment about this hinge, then the no. What you're saying will not work out.
not about the hinge, sir. The middle support.
If you take moment about the middle support, you will get a reactions between RA and RB.
Yes, sir.
But
I
why
got
are
a
we?
relation.
No, but why are you doing it like this? Let us look at it. I have a 2D problem. All the known forces are in the same direction. How many equations of equilibrium do I have?
If you say like that, that is indeterminate. But if I write equation, I can solve it.
Okay, try. Go ahead. Once you do it.
No, sir. I'm asking, is that correct or not?
I don't think it is correct.
Okay.
Yes, sir. By that way, answer does not come, sir, because same equation created by that moment, sir.
You'll start getting linearly dependent equations after some time. Two
Yeah, sir.
independent
Yes.
equations and the others are all dependent equations.
Yes, sir.
Sir, we have to replace the hinge when we break the two parts from two reaction forces.
You will have two reaction forces, yes, equal and opposite.
Sir, then first find support and then again start with BMD. Oh, sorry, then, all the diagram.
1 minute, let me project my step-by-step solution. Do something like this. Something like this. So basically what I have
Yes,
done,
sir.
broken it into two, calculated RA, RB will be plus minus, this is upwards, this is downwards, and draw the bending moment and shear force diagram of the two beams independently and then join it.
Sir, if I remove the rod, the slender bar from only the supports, then will there be any force at the hinge?
Which rod? I don't understand. So which rod are you talking about?
The complete rod, sir.
This is my beam.
Yes, sir. Complete beam.
So you want to remove the beam from what?
Support, sir, and draw the FBD.
If you remove the beams, if you remove the supports, you will have three unknowns.
Yes, sir. I got.
RB, RC. Basically, these are the values that I have calculated, but I could do that only after breaking it into two.
No, sir. I'm asking after removing that, if I don't break it into two parts, then will I get any force at the hinge?
But how will you find out the value of the three reactions? That is my first question.
You get a y direction reaction RA, RB, RC plus equal to something 10 into 88.
Oh, one equation.
Yes, sir. Then you conserve moment about RB.
Two equation.
The middle. Conserve moment about first RA.
But the three equations that you write are not linearly independent. You only have two independent equations. You can write as many equations as you like. You can write infinite number of equations, but we are not looking for number of equations. We are looking for number of independent equations. This is a case of a 2D equilibrium. All the forces are aligned in the same direction. You cannot have more than two independent equations of equilibrium.
Okay.
Yeah, so I think this is the best way of doing it, that break it into two, calculate the reactions,
Yes,
draw the
sir.
draw the BMD diagram of the two independently, join it. To check that your answer is right, the bending moment at the hinge should be 0.
Sir, we will take reference same for both the parts.
If you take same, be careful while drawing the bending moment diagram of the second one. Then all your equations will be in terms of x minus 2. You can take, my advice is to take two separate, just draw the two bending moment and shear force diagrams, imagining that the other one does not exist only. Once you have calculated the value of RB, which are the shear reactions at the hinge point, draw the first free bending moment and shear force diagram, imagining that the second one does not exist, and vice versa for the second one.
Okay,
Choosing
sir.
the same one will actually lead to some problem while drawing the, writing the equation. Then you have to write everything in terms of x minus 2, not x.
Okay, sir.
Sir, I have a doubt in internal hinge.
Okay.
Sir, when we separate the two parts, then is that possible that the there is bending moment at one part on the internal hinge and bending moment at other part on the hinge, and both add up to give 0, or individually they are 0 for both the parts?
Individually they are 0. So RA will have, when you draw the bending moment diagram of R member AB, so RA, so this is part is A, this is B, so it will come out to be 0 individually.
Okay, sir.
Why so, sir? Why?
This is how hinges are designed actually. A,
Okay.
B, this is B mainstream, C, this is again. So I was saying that if you draw the bending moment diagram of AB and BD, individually at bending moment at B will be 0 for both the cases.
Means this is the assumption or the result on which we arrive means. How will we find RA and RD if we do not assume individual moments to be 0?
How will I find RA and RB?
RD, Delhi.
It is individually 0, otherwise you cannot find
Means
RA.
that is the assumption. We cannot prove that from calculation.
No. I mean, you have to start somewhere, right? You have to start
Okay,
somewhere.
okay, sir.
Actually, that is not assumption, that is simplification. That is a correct term, I think.
Okay, sir.
It should look something like this. Okay, so now please try to solve this. I think it should be doable once you understand that they have to be separate. I think with this we have discussed every type of problem that was there in problem sheet A. So 6A, whatever type of problems was there, I think you should be able to solve if you have followed today's class. Now, I want to give you so any questions about this, or I can wind up the class? If not, then I want to give you a fun exercise. So this week there is no assignment, yes. So I want to give you an assignment which will carry no marks, but it should be very interesting to you. So now, if you look at this bending moment diagram, okay, what would happen if all the load was pointing upwards? What would the bending moment diagram look like?
Sir, are you drawing
Sir, you are
something?
presenting something.
Oh, sorry, my bad. I thought I was presenting a screen. So as I said, this is the answer for this problem, okay? Now, please try
Sir,
to
where is
solve
the graph?
which graph? Is it visible?
Yes, sir. Yes.
So try to solve this. If you can't solve, let me know. We'll have one more, I think, tutorial / doubt clearing for this topic. But I think with this
Sir,
problem, you should be able to solve all the problems. Yes?
sir, please repeat once again.
So I was saying that if you should be able to solve all the problems in this problem sheet, because all the different types, at least we have discussed all the different types that are possible. There are not too many problems that are possible. And this is the answer for this problem. I suggest that you try to solve this completely. If you are still not able to solve it, in the next class, I will, or I can write a scan is perhaps the only part that is a little bit difficult for the class. Okay, so try to solve it. If you can't solve it by Monday morning, I will upload a detailed solution of this problem. Now, I was saying that, is it okay? Everybody will try, and by Monday, I will upload a detailed.
Yes, sir.
I will upload a detailed solution. Now,
Yes, sir.
I was saying that imagine what would happen if this load that is in this problem, instead of pointing downwards, was pointing upwards. What would my what would my bending moment diagram look like? It would look
Sir,
like,
we will replace
The mirror image
10
of
by minus 10.
it would look something like this. Yes, the one that I have drawn. Just the mirror image, as you say.
yes, sir.
Now,
Yes, sir.
look carefully. Does it resemble some alphabet? Can I write some
Yes,
alphabet
sir.
like this, and I draw a
W,
line?
W.
It can,
W, sir. W.
it can be W also, or if I
A.
draw, it
A,
can
yes, sir. A.
A also.
Yes, sir.
So, yes. So the assignment for all of you is to try to think of a loading such that the first alphabet of your name shape is either the bending moment diagram or the shear force diagram.
Sir, mine starts with A only.
Yes, sir.
Yes, sir.
Yes, sir.
Think,
Mine
My
also.
first letter is S. How
so
it
think of some other load where you are getting A type without a hinge or something. Try.
So
Okay, sir.
they can
Sir,
use the first
my letter
of
is
the
D.
surname.
Sir, but
How
there
can I
can be
get
many letters for which there cannot be any bending moment diagram.
Which one, for
Yes, sir.
example?
For example, O, sir.
I am stopping the recording.
D, sir?
Sir,
D.
T.
Sir, A, S, D, O.
Hey, D कौन बोल रहा है नहीं होगा? D तो we have done in the class 5 minutes ago.
Sir, S, sir. S.
This is D. D. Why not?
Sir, not like this, sir. I'm saying
C is also done.
line is perpendicular to the
Both are
axis.
same.
अच्छा,
Sir,
perpendicular
S
to the.
can be possible.
Yes, sir.
हाँ, मतलब you I'm giving you liberty that we can look at D sleeping or standing. That is fine. Okay.
E would be a bit difficult. I think.
E, then sir, K.
Sir, S can be possible, sir.
I think with some creativity, any alphabet should be possible. Please try. This is an assignment which doesn't have any marks, but if you are able to think of it, please post it in the MS Teams. I think it will be fun. It will also improve your understanding of this topic if you are able to do this.
Yes,
You can also try linear and other type of loads, but I don't think you will have to go for any loads. More or less, with point load, uniformly distributed load, and moment, you should be able to, with some imagination, be able to design a load such that either the bending moment or the shear force diagram will look like the alphabet of your name. Okay, please try that. It will be interesting, I think. And once you get it, take a picture and post it. I will start a thread in this MS Teams and start posting it. I think, let us see, it should be interesting.
Yes, sir.
Okay, then I think we can wind up, stop recording.